This lecture begins a very important step in space plasma physics. Up to this point, the discussion is focused on what plasma is, why it is different from ordinary matter, and where it exists in near-Earth space. Now the focus shifts to a more fundamental question. How does a single charged particle move in electric and magnetic fields? This question is central because all large-scale plasma behavior, including currents, particle trapping, aurora, and transport, ultimately grows out of the motion of electrons and ions. So this lecture provides the microscopic physical foundation for many of the larger plasma phenomena that appear later in the course. The first 3 lectures naturally lead into this one. The first lecture introduced space plasma physics, its scope, history, and relevance. The second lecture explained the basic plasma properties, including quasi-neutrality, Debye shielding, plasma criteria, and plasma frequency. The third lecture explored the near-Earth plasma environment, including the solar wind, bow shock, magnetosphere, aurora, and current systems. All of those regions and phenomena are populated by charged particles, so the next logical step is to understand how those particles actually move. This is why particle motion must be studied. Space plasmas are made of electrons and ions, and these particles do not behave like the molecules of a neutral gas. Their motion is controlled by electric and magnetic fields. Many important space plasma phenomena, such as ring current formation, auroral precipitation, and cross-field transport, begin at the single particle level. Understanding individual motion gives the physical basis for later fluid and kinetic descriptions. This lecture has a clear set of goals. The first goal is to understand why plasma physics uses different theoretical approaches instead of one single universal description. The second is to identify when the single particle approach is useful. The third is to write and interpret the equation of motion of a charged particle in electromagnetic fields. Then the lecture moves to the basic properties of gyration in a uniform magnetic field, including gyrofrequency, gyroradius, guiding center, and pitch angle. Finally, the lecture explains how a perpendicular electric field causes guiding center drift and how the E cross B drift is derived and interpreted physically. The course book shown on the slide is the main reference, and it is useful to keep that in mind because the lecture structure follows a standard plasma physics development. Plasma physics requires different theoretical approaches because a plasma is not simply a collection of independent particles moving in fixed external fields. Charged particles respond to electric and magnetic fields, but they also create charge separation and currents. Those, in turn, generate internal electric and magnetic fields. These self-generated fields act back on the particles again. So plasma motion involves feedback between particles and fields. If all field were only external and fixed, the problem would be much simpler. But in a real plasma, the internal fields make the problem richer and more difficult. In principle, it is possible to write the equation of motion for every particle. In practice, that exact approach is not useful because the particles are coupled through the electromagnetic fields generated by all the others. Usually, the interest is not in the motion of one specific particle, but in average quantities such as density, velocity, current, and temperature. That is why approximations are needed, and that is why plasma physics is built on different levels of description. The 4 main theoretical approaches are summarized on this slide. The single particle approach studies the motion of one charged particle in prescribed electromagnetic fields. This is the simplest and most intuitive starting point. The magnetohydrodynamic approach, or MHD approach, treats plasma as one conducting fluid and is very useful for large-scale, low-frequency phenomena. The multi-fluid approach goes one step further and treats electrons and ions as separate fluids, which becomes important when the 2 species behave differently. The kinetic approach is the most detailed and studies the particle distribution functions in phase space rather than only average quantities. The reason for beginning with the single particle approach is that it provides the clearest physical picture. Before studying collective plasma motion, it is essential to understand how one charged particle behaves under electric and magnetic forces. The single particle approach is useful when collective effects can be neglected or treated as secondary. It is especially helpful in low-density plasmas or in situations where strong external magnetic fields dominate the motion. In such cases, the path of a charged particle can be treated approximately independently, at least as a first step. The figure on the slide visually supports this idea. The upward blue arrow marked B represents the magnetic field direction. The red and blue trajectories show charged particles spiraling around the magnetic field lines rather than moving straight across them. This makes an important point immediately clear. Magnetic fields organize motion geometrically. Even in plasmas where collective behavior is important, this single particle picture remains extremely instructive because it shows how fields shape motion before more advanced plasma descriptions are introduced. Two basic forces act on charged particles. A charged particle at rest in an electric field experiences the electric or Coulomb force. This is written as Fc equals QE. In words, the electric force equals the particle charge multiplied by the electric field. A positive charge is pushed in the direction of the electric field, while a negative charge is pushed in the opposite direction. A moving charged particle in a magnetic field experiences the Lorentz magnetic force. This is written as Fl equals Q times V cross B. In words, the magnetic force equals the charge multiplied by the cross product of velocity and magnetic field. This means the force is perpendicular to both the velocity and the magnetic field. The figure on the right illustrates these directions. The particle is shown with its velocity, the electric field, the magnetic field, and the resulting force. The key point is that the magnetic force changes direction of motion, while the electric field can change speed as well as direction depending on the geometry. The equation of motion of a charged particle is obtained by applying Newton's second law to the total electromagnetic force. The result is mass times dV by dt equals charge times the quantity E plus V cross B. In symbols, mdV by dt equals Q times E plus V cross B. Each symbol has a clear physical meaning. M is the particle mass, Q is the charge, V is the velocity, E is the electric field, and B is the magnetic field. This is the fundamental equation of single particle dynamics in plasma physics. Every result in this lecture, including circular motion, helical motion, and drift motion, comes from this one equation. The simplest possible case is chosen first by setting the electric field equal to 0. Then the equation of motion becomes mass times dV by dt equals Q times V cross B. This means the acceleration is always perpendicular to both the particle velocity and the magnetic field. That has a very important consequence. A force that is always perpendicular to the velocity cannot change the speed of the particle. It can only bend the direction of motion. So a magnetic field does not directly increase or decrease the kinetic energy of a particle in this static case. Instead, it guides the motion by curving the trajectory. This is why magnetic fields are often described as controlling the geometry of the particle path, rather than acting like ordinary accelerating forces. This slide explains mathematically why a magnetic field does not change kinetic energy. Begin with the equation of motion and take its dot product with the velocity vector. On the left side, this gives mass times dV by dt dotted with V. On the right side, it gives Q times V cross B dotted with V. Now use the geometric fact that V cross B is perpendicular to V. Because perpendicular vectors have 0 dot product, the right-hand side becomes 0. So mass times dV by dt dotted with V is 0. Next, use the standard identity that the time derivative of 1/2 mv squared is equal to mass times dV by dt dotted with V. Therefore, the time derivative of 1/2 mv squared is 0. That means 1/2 mv squared remains constant. The conclusion on the right side of the slide states the physics clearly. A static magnetic field does not change particle kinetic energy. It only bends the trajectory. This is one of the most important ideas in charged particle motion. Now the magnetic field is chosen to be uniform and directed along the z-axis. This is written as B equals capital B times z hat. This is a very useful geometry because it simplifies the mathematics and separates the motion naturally into two parts. The magnetic force affects only motion in the x, y plane. The z component is unaffected. So the motion divides into perpendicular motion in the x, y plane, and parallel motion along the z direction. This separation is one of the most useful organizing ideas in plasma physics. It allows the perpendicular and parallel behaviors to be studied separately and then combined into one full particle trajectory. This slide converts the vector equation into component form. Write the velocity as Vx, Vy, and Vz. Since the magnetic field is along the z-axis, the cross product V cross B could be worked out explicitly. The result is Vyb in the x direction, minus Vxb in the y direction, and 0 in the z direction. Substituting this into the equation of motion gives three component equations. The first is m times Vx dot equals qbvy. The second is m times Vy dot equals minus qbvx. The third is m times Vz dot equals 0. The first two equations are coupled, which means the x and y components influence each other. These two equations describe the motion perpendicular to the field. The third equation shows that the parallel velocity remains constant. So already, the mathematics is confirming the physical picture introduced on the previous slide. This slide derives the gyrofrequency. Start with the first component equation, m times Vx dot equals qbvy. Differentiate it once more with respect to time. That gives m times double dot Vx equals qb times dot Vy. Now use the second equation, where dot Vy equals minus qb over m times Vx. Substituting that into the previous line gives double dot Vx equals minus qb over m, all squared, times Vx. By the same method, the y component becomes double dot Vy equals minus qb over m, all squared, times Vy. These are simple harmonic oscillator equations. So the perpendicular motion is oscillatory, with angular frequency omega g equal to qb over m. This angular frequency is called the gyrofrequency or cyclotron frequency. The figure on the slide reinforces the result physically. The magnetic field is shown directed out of the page. The electron moves in one rotational sense, and the ion moves in the opposite sense, because their charges have opposite signs. The electron orbit is much smaller, which reminds us that lighter particles generally have faster gyromotion and tighter orbits than heavier particles. The physical meaning of gyrofrequency is straightforward but very important. Gyrofrequency tells how rapidly a charged particle circles around a magnetic field line. It becomes larger when a magnetic field is stronger because the magnetic force is stronger. It becomes smaller when the particle mass is larger because heavier particles respond less rapidly to the same force. That is why electrons rotate much faster than ions. The sign of the particle charge determines the sense of rotation. Positive charges rotate one way, and negative charges rotate the opposite way. The figure again helps make this visual. The opposite arrows show opposite rotation, while the much smaller electron orbit emphasizes the much faster electron response. The position equations for the perpendicular motion are now written explicitly. X minus x0 equals Rg sine omega gt, and y minus y0 equals Rg cosine omega gt. These are the standard equations of a circle. The point x0, y0 is the center of the circular orbit. This point is called the guiding center. That idea is extremely important. The particle is not required to circle around the coordinate origin. Instead, it circles around its own guiding center. Later, when electric or magnetic inhomogeneity is added, the particle will still gyrate, but the guiding center itself may move. That is how drift motion is introduced. So this slide is where the idea of separating fast orbit motion from slower center motion becomes clear. The radius of a circular orbit is called the Gyroradius or Larmor radius. It is first written as Rg equals v perpendicular divided by the magnitude of omega g. Replacing the magnitude of omega g by absolute value of q times b over m gives Rg equals m times v perpendicular divided by absolute value of q times b. This formula contains a lot of physics. A larger perpendicular speed gives a larger orbit because the particle tries to move farther before the magnetic field bends it. A larger mass also gives a larger orbit because heavier particles are harder to bend. A stronger magnetic field gives a smaller orbit because the magnetic turning force is stronger. The figure on the right shows the orbit radius as a real geometric distance from the center to the particle. This is useful because it helps students see gyroradius as a physical spatial scale, not just a formula. The last statement on the slide is very important. Ions usually have much larger gyroradii than electrons because ions are much heavier. Perpendicular motion alone gives a circular orbit, but there is also motion along the magnetic field. From the third component equation, m times vz dot equals 0, so vz, or the parallel velocity, remains constant. That means the particle circles in the plane perpendicular to the magnetic field while simultaneously moving uniformly along the magnetic field. Combining these two motions produces a helix. The figure on the right shows this very clearly. The straight horizontal arrows represent the magnetic field lines. The orbit wraps around them in a spiral, showing that the particle is advancing forward while also circling. This helical motion is one of the most basic and recurring pictures in plasma physics. The pitch angle measures the relative importance of perpendicular and parallel motion. It is defined as alpha equals tan inverse of v perpendicular divided by v parallel. If the pitch angle is small, the motion is mainly along the magnetic field. If the pitch angle is close to 90 degrees, the motion is mainly perpendicular to the field. So the pitch angle tells how the velocity is distributed between motion across the field and motion along it. The figure at the bottom helps visualize this. The magnetic field is drawn horizontally. The helical orbit is shown around it, and the velocity components are resolved into perpendicular and parallel parts. The angle between the particle motion and the magnetic field direction is the pitch angle. This quantity will become even more important later in trapped particle motion and magnetic mirror effects. This slide summarizes motion in a uniform magnetic field. A magnetic field does not change the speed of the particle, because the magnetic force is perpendicular to the velocity. It bends the trajectory, producing circular motion in the perpendicular direction. The parallel motion remains uniform. Together, these produce a helical orbit. The four key quantities are guiding center, gyrofrequency, gyroradius, and pitch angle. These should be seen as parts of one connected picture, not as isolated definitions. The guiding center tells where the orbit is centered. The gyrofrequency tells how fast the particle rotates. The gyroradius gives the size of the orbit, and the pitch angle tells how the motion is shared between perpendicular and parallel directions. Now an electric field is added. In real plasmas, electric fields are often present together with magnetic fields, so the full equation must be used again. Mass times dV by dt equals charge times the quantity E plus V cross B. The important change is not that the particle stops gyrating. The particle still gyrates, but now the guiding center itself can move. This motion of the guiding center is called drift. So instead of a particle circling around a fixed center, the particle circles around a center that may itself move through space. The first and most important case is when the electric field is perpendicular to the magnetic field. That leads to the E cross B drift. The electric field is separated into two parts, a component parallel to the magnetic field and a component perpendicular to the magnetic field. The parallel component causes direct acceleration along the magnetic field, written as m times v parallel that equals q e parallel. In words, a parallel electric field pushes the particle along the field line. the perpendicular component behaves differently. It does not simply accelerate the particle forever across the field. Instead, it changes the orbit in such a way that the guiding center drifts across the magnetic field. This is one of the most important conceptual lessons of the lecture. In a magnetized plasma, an electric field perpendicular to B does not simply cause straight-line acceleration. It modifies the gyration and produces a sideways drift. The last point on the slide adds a realistic space plasma note. In many space plasmas, sustained parallel electric fields are often small because electrons move very easily along magnetic field lines and tend to neutralize such fields rapidly. This slide sets up the derivation of the E cross B drift. The magnetic field is taken along the z-axis, and the perpendicular electric field is taken along the x-axis. This geometry is chosen because it makes the algebra simple while preserving the physics. With this choice, the component equations become m times vx dot equals qbvy plus qex, and m times vy dot equals minus qbvx. Compared with the pure magnetic case, only one new term appears, qex. That constant electric term is what shifts the center of the motion. So this slide is preparing the mathematical structure for the drift derivation. This slide derives the drift mathematically. Begin with the second equation and differentiate it with respect to time. That gives m times double dot vy equals minus qb times dot vx. Next, replace dot vx using the first equation. Dot vx equals qb over m times vy plus qex over m. Substituting this into the previous result gives double dot vy equals minus qb over m, all squared, times vy, minus q squared bex over m squared. Now define omega g as qb over m. Then the equation becomes double dot vy equals minus omega g squared times the quantity vy plus ex over b. This is still harmonic motion, but not around zero. It is harmonic motion around a shifted value. That shift is the mathematical sign that the guiding center is moving. The drift velocity is now extracted from the shifted oscillation. Define a new variable, vy prime, equal to vy plus ex over b. Then the equation becomes double dot vy prime equals minus omega g squared vy prime. That is the usual harmonic oscillator equation again. So the motion is still circular in nature, but now centered around a moving guiding center. For this specific geometry, the drift velocity is minus ex over b in the y direction. In general vector form, the result is v equals e cross b divided by b squared. This is the E cross B drift. It is one of the most fundamental results in plasma physics. It gives the velocity of the guiding center when uniform electric and magnetic fields are perpendicular to one another. One of the most remarkable features of the E cross B drift is that electrons and ions drift together. This may seem surprising at first, because electrons and ions have opposite charges. In a pure electric field, they would accelerate in opposite directions. But in crossed electric and magnetic fields, the geometry of the Euro motion changes the result. The electric field makes one half of the orbit larger and the other half smaller. Because electrons and ions rotate in opposite senses, the effect of opposite charge is balanced by opposite sense of rotation. The net result is that both species acquire the same drift velocity, v. This is why the E cross B drift is often a bulk plasma drift. It moves the plasma as a whole across magnetic field lines without directly producing strong charge separation. The physical interpretation of the E cross B drift becomes clearer from the orbit shape. During one half of the Euro orbit, the electric field accelerates the particle, so the speed becomes larger and that side of the orbit becomes larger. During the other half, the electric field decelerates the particle, so the speed becomes smaller and that side of the orbit becomes smaller. This makes the orbit asymmetric. Because the two halves are no longer equal, the center of the orbit shifts sideways. Repeating this process every gyrocycle leads to a steady drift of the guiding center. This is the most intuitive way to understand the E cross B drift. The drift is not produced by destroying the circular motion. It is produced by distorting the circular motion asymmetrically. The E cross B drift is extremely important in real space plasmas. It is one of the major mechanisms for transport across magnetic field lines. Because electrons and ions move together, it can carry plasma as a bulk medium across the field without immediately creating large charge separation. This drift is important in the ionosphere, in the magnetosphere, and in large-scale convection patterns driven by electric fields. So although the derivation began with a single particle, the result applies directly to large plasma systems and helps explain observed plasma motion in space environments. The conclusions of the lecture bring the main ideas together. Plasma physics uses different theoretical approaches because the complete mini-particle problem is too complex to solve directly in most cases. The single-particle approach is the most direct starting point because it gives the clearest physical insight. In a uniform magnetic field, a charged particle undergoes gyration. Its kinetic energy remains constant, while the magnetic field bends the trajectory. The motion is described by gyrofrequency, gyroradius, guiding center, and pitch angle. When a perpendicular electric field is added, the guiding center drifts, and the resulting E cross B drift becomes one of the most important motions in space plasma physics. The assignment reinforces both mathematics and physical understanding. The first question checks whether the idea that magnetic force does no work is properly understood. The second focuses on gyrofrequency and gyroradius, and how these depend on field strength, charge, mass, and speed. The third asks for the physical origin of the helical orbit. The fourth requires the derivation of the E cross B drift in the chosen X and Z geometry. The fifth asks for the physical explanation of why electrons and ions drift in the same direction. Together, these questions help connect derivation, geometry, and physical interpretation. This lecture has built the first true dynamical picture of particle motion in space plasma. The key image to keep in mind is a charged particle spiraling around a magnetic field line, possibly moving along the field, and when appropriate electric fields are present, drifting sideways through space. This is the foundation for more advanced motion in non-uniform fields and for later topics such as polarization drift, gradient drift, curvature drift, and trapped particle motion. The essential picture from this lecture should remain clear: fast gyration, possible motion along the field, and slow guiding center drift.